I've been in the oil industry now for 18 years. Hard to believe, looking at my youthful face. But I started with Schlumberger Drilling and Measurements. I did 13 years with them, coming through MWD, directional drilling, and then some management roles. And then I joined NOV 5 years ago, and specialties really drill bits and drilling optimization. And prior to this position, I was the Director of Drilling Solutions for downhole for the Eastern Hemisphere. So I'm going to talk to you today about vibration. Leo has asked me to come and talk to you about that. A lot of energy is wasted in drilling, in vibration, and if we can control the amount of vibration we have, then we can put that energy back to the drill bit and see the benefits in increased ROP and therefore savings to your bottom line. So it shouldn't take more than an hour or so, certainly not much more than an hour. Please feel free to stop me at any time and ask questions. I don't speak Bahasa Indonesia, so I'm going to have to speak in English. So if I'm going too fast or too quiet or you don't understand what I said, please just stop me and I'll try and explain it in a different way if I can. All right. So I think you know the rest of the team, Johnson, Nerissa and Leo, who are part of the downhole sales team here. So we've spent a lot of money and time on vibration the last few years, and we're now able to do vibration prediction, vibration measurement, vibration mitigation, leads to optimization, and hopefully leads to savings for you, the customer. Here's just some examples of the results of unwanted vibration. This is a typical bit dull from a torsional situation, stick slip, if you like, in its worst form. You've got whirl, where you're missing blades and cutters from bits. We've got premature failure of drill string components due to fatigue through bending. We've got excessive torque applied to tool joints because of torsional vibration downhole. And this is probably the hardest picture to see. There's actually a crack all the way through this connection here, and this stabilizer and bit is just hanging on by a very small piece. So a lucky escape for that customer. So these are all the unwanted effects of vibration on downhole components, not to mention the loss of penetration that you get through not putting energy to the bit. So on the prediction side of things, we've got a software package called Vibroscope, which does a finite element analysis of the BHA. We input the trajectory, the BHA in terms of the geometry, as accurate as we can get it, and some mud information. And what we can do with this is we can predict the parameters, surface parameters, weight on bit and RPM, that are most likely to give you torsional, axial, and lateral vibration downhole. Okay? So we can run this ahead of time. We can come up with the driller's roadmap. Say, in these, avoid these parameter combinations if you want to give yourself the best chance of avoiding the vibration. So this one at the top, you can look at the string modes and see where the actual lateral and torsional nodes are going to be. This is a clearance plot and tendency plot, so we can see how the BHA is going to lie in the hole. The third one here is bending stresses. So this particular BHA had severe bending stress down at the bit, which could put excessive side force loadings on the motor bearings and cause you problems. And then the last one is a compression. This is side force, so this is a bending stresses plot. So with this we can see changes in the BHA when you go from one diameter to another. Could potentially be a weak point in the BHA. So it's all about engineering in or engineering out the potential for problems using the software. Typical output from the software would be a plot like this. This is just one of many. This is increasing depth here on the y-axis. This is surface RPM on the x-axis. And what these lines represent are nodes of instability, basically. So if, for example, I started drilling here with my RPM at a constant rate, eventually when I get down towards this sort of depth, I'm going to start to cross these lines. What this means is I have a high probability of inducing that kind of vibration. Now, I need something to start it off. So if I land on this torsional node, I may see torsional vibration, I may see nothing. But if I have some stabilizers that are digging in, or a drill bit that's digging in and starting that resonance off, then at this RPM, that drill string is likely to go into resonance, and I could end up with a full stick-slip situation. So what this chart enables you to do basically is to drill through and sort of navigate yourself around these lines and plot a path through down to TD, avoiding these situations. And this is the blue lines on here. So if you stay in these blue areas, that's the safest place to be. The program also puts out the torque and drag, so we can plot up all the predicted torque and drag as well. So this is just showing you the torsional is in red. The lateral bands tend to be concentrated in one particular RPM range, and they're dependent on weight on bit. So the larger spread your weight on bit, the thicker this band is going to be, and then axial in blue. So here's an example of a post-analysis of an application. And what we're looking at here is we're looking at a time log and a depth log for the same events. So we see here, this is RPM as measured by our black box tools, and we're going to come on to them a little bit further in the presentation. Basically, we see a fairly steady RPM down to this point here, and the stick-slip variance is quite small. At this point here, we go from drilling to reaming. Okay? So we go from 140 RPM surface to 60 RPM surface when we're doing the back reaming. So if you look at the signature of the downhole vibration when we're reaming, it's horrendous. Right? And when you go back to vibroscope and you have a look at what's happening, well, at 140 RPM when we were drilling, we were quite a long way from this torsional line. When they went to 60 RPM back reaming, they dropped onto a second line of torsional instability, and the BHA went into full-on stick-slip. So perhaps 60 wasn't a good RPM to back ream at. Perhaps 75 or 80 or less would have been better. So this just doesn't guarantee you're not going to get anything, but it gives you a better idea of where to be. And often when we look at post-studies of failures and you see horrendous stick-slip, okay, what do? Well, let's increase RPM by 15. So they increase RPM by 15, they end up on another line. So okay, let's decrease RPM by 30, and they end up on another line. What this software allows you to do is pick the pieces in between, so there's less guesswork involved. So on the measurement side of things, we have three tools. The first one is black box. It's a small, self-contained, ice hockey puck-sized instrument that can either sit in its own dedicated string subs or bit subs, or we can put it into other downhole components. So we put it into the bit box of motors, we put it into under-reamers, we put it into stabilizers. Basically anywhere where there's enough meat or enough metal that you can make a pocket, you can put the puck inside. So what this measures is, it's a single axis accelerometer, and from that we can get the maximum lateral shocks, an RMS shock value, torsional variation, which is going to give us a stick slip, we get RPM, and we get temperature. So we get 5 read instruments. How this differs from MWD tools is the speed. We sample at 400 hertz, so we're taking 400 samples every single second. We are statistically analyzing those and recording those to memory. An MWD tool, from my Schlumberger background, I know that the tools are set to record at 50 G. So any shocks less than 50 G you don't see. They're transmitted every D point. So if you get a shock value coming up once per frame, then you get to see the information once every 1 minute, 1.5 minutes. something like that, and it's all average values over the last time it was done. This is going to record everything, and if you see everything, then you can manage what's going on. If you don't see it, then you can't. And there's a saying in real time is too late, right? It's too late to react when you see it from the MWE. What we do with this data is we use it for the next well to engineer out the problems that have occurred on this one. Okay, so it's not going to help you today, but it will help you tomorrow and every other well after that you drill, and you can take those lessons going forward. So the batteries last for 200 hours, which is about 10 days, and that's usually long enough for most applications. The beauty of the black box is you can put it anywhere. Anywhere that you can put a sub, you can put the black box tool. So if you're running a motor, ideally you run it below the motor, that gives you an indication of what the tool is doing. Somewhere in the BHA and then up in the drill pipe. When you have an unexplained drill pipe twist off and no one understands what's happening, when we put these tools in afterwards, you can see the drill pipe undergoing horrendous whirl or stick slip or vibration that no one knew was going on. So this allows you to see all the way up the string and maybe make some design changes for the next well. So this is really sort of getting the big picture about what's happening. Putting that into practice then, what we're looking at here is a post-job analysis where we've got the lithology and we've got the vibroscope done. And what we're looking at here is, this is the surface torque in blue, weight on bit in red. This is the black box RPM data from the BHA position. And in red we have black box RPM data from the near bit position just below a drilling motor. Then in green you can't really see, we've got the gamma ray, ROP lithology, and then this is the vibroscope. So we've got some indication at surface that something is not right. We've got some torque from the top drive, and anyone who's on the rig floor is going to hear this, right?
What's the unit of vibration?
G. Well, RPM is in RPM, and these are in G. Right. G. Yeah. The gravity. So if you're a fighter pilot and you pull 10G, you black out. So we've got correlation between the surface erratic torque, downhole RPM variance, both in the string and down at the drill bit below the motor. Okay? In this event here, for 100 feet, a complete stand, the string has stalled. Okay? So we've got full stick slip from 0 to 100 RPM or so in the string. But if you look here, the bit is still turning. So the bit is not stalling. The motor is still turning the bit. So this is a string stall, it's not a bit stall. You know, often the bit gets blamed for a lot of things, but in this case you can prove what's happening and you can make changes to, you know, some people would say the bit's no good, it stalls all the time. Well, no, not in this case. Right? If you look at the vibroscope, this is the actual RPM used. So throughout these first few hundred feet, they have one constant RPM that they're using. But obviously there are some surface indications that there's some torsional events going on. So perhaps they've decided to make a change in the RPM to counteract that surface problem. Well, they changed it there. There was no real change on surface. But downhole, things changed a lot. And you see what they did. They landed right on this line of instability and correlated with a string stall. Okay? After that stand was finished, they increased the RPM to beyond the previous limits, and the torque went away quite happily. Both RPMs below and above the motor were quite smooth, but now we've started to introduce a lot of lateral vibration. And that seems to have come from nowhere, apart from when you look at the lithology now, and I'm going to have to trace it with my finger. The gamma ray is coming down here, and then it's getting really clean, and it's corresponding to a very hard limestone. So this is formation-induced vibration. So I can't do much about that, because every time I drill your well, I'm going to go through that formation. What I can do is I can plot the parameters which give me the least amount of vibration going through that formation. So in the future, when I come to it, I can say, okay, this is my limestone, this RPM, this weight on bit gave me the best combination to drill that. And that's where we come to this sort of 3D contour plotting. So in both of these graphs, ROP is represented by the colours, purple being the slowest, red being the fastest. Plotted here, this is depth versus compressive strength. This is this band of hard limestone at 6,000 whatever feet, all the way out to 60,000 psi. So very hard, but actually quite drillable. You know, when you look at the ROP, it's not so bad because limestone can pre-fracture and it can be quite drillable, it looks very hard. Interestingly, what this plot tells me is from 10,000 psi compressive strength onwards, this is weight on bit. It doesn't matter how much weight I put on it, I'm never going to drill any more than between 20 and 50 feet an hour. So this application is bit constrained, right? At 60,000 pounds weight on bit or whatever it is, if the formation is more than 10,000 psi strength, I'm not going to drill any quicker than 50 feet an hour. So if I want to drill quicker, I'm going to have to choose a different bit. Okay? So this is the kind of the post-run analysis we can do. It's a recorded mode product. So is the Blackbox HD, and so is the EMS, which I'll come on to in a minute. And the argument we always get is, well, if it's not real time, what good is it for me? Okay, well, here is the black box data, and this is the associated data coming from the MWD tools. You miss so much information when you're getting updates like this compared to this. You can't engineer out for the next well based on this information. Based on the black box analysis, you can make changes to your BHA if you know what's causing the problems. You can make changes to your parameters because you can see instantly what happened when you apply different surface parameters to the downhole information. This information you can't do anything with. It's good for, oh, I've got level 3, therefore I need to stop drilling and pick up off bottom and do whatever. That's about it. So this is the second tool we have. It's called the Blackbox HD. Now we have true at the bit measurements now. Okay. With the Blackbox plug, we could put it near the bit. We often get pushback from the DD companies about adding components below rotary steerable tools or below the motor. Obviously it changes the bit to bend distance and the steerability issues. So with this one, well, you don't need a separate sub now because the tool fits directly inside the bit. Plus this is a bit of a beefed up tool. We're now sampling at 800 Hertz instead of 400. And we've added magnetometers to give us a true RPM. And we've got 4 accelerometers, including one in the axial plane. So now we can look at axial. We've got 3 inclinometers for lateral, and we've got 2 magnetometers to give us the torsional stick lip RPM and everything else. It doesn't take a lot of energy to run it. 60 to 75 psi pressure drop in the bit, so it slots in quite easily, and again it has about 200 hours of life. So with this one you can really see what's going on at the bit. Okay. So here's a comparison between what you see with the black box plug. This is RPM, so we've got some quite severe torsional vibration going on here. It's running from about 50 to 200 or so variation, so quite serious. An analysis with this, we would say, okay, we've got severe torsional vibration, but it's not stick slip because it doesn't go to 0. When we add in the HD data, we now have the ability to record the minimum, the mean, the maximum, standard deviations, much more information. Now we see actually the minimum value does go to 0 quite often, and the maximum value is up in the 250. So this range that we thought was from 50 to 200 is actually from 0 to 250, maybe even worse. So it's more severe than, that's due to sampling and averaging and whatever. So if you run an HD, it gives you a better idea of what's going on. EMS is the third tool. This is the enhanced measurement system, and this is now a collar-based tool. It measures much the same things as the HD. So we've got the 4-axis accels, 2 magnetometers, But now we've added weight on bits. Yeah, okay, you've got probably a good idea of what the weight on bit is because you're vertical. When you're highly deviated, who knows? You might be getting 15% of your weight down to the bit. With this tool, we can tell you exactly how much weight is getting down there. And annular pressure, obviously, for looking at hole cleaning and things after the event as well. Much the same specs as the HD, 800 Hertz. The battery life is a bit better, up to 350 hours. So you can stay on the rig for quite a long time. Here's just some looking at the data. The black box says 180 to 250 with the near bit and 70 to 160 in the string. HD EMS just opens everything up. If the delta RPM goes above 1, that's an indication that you have stick slip, right? 0 string stopping. The way our tools work, they're sampled and averaged. Well, they're averaged every average every 2.5 seconds. So basically, if the tool sees any rotation in that window, it will record that rotation. If it doesn't see any rotation, it will record a 0. So we did a job in the UK for Exxon last year, and they were in the hole for 10 days, and they had horrendous torsional vibration throughout the whole run. When we added up all the times that the tool recorded 0, we came up to 3 days, 72 hours of non-rotation when they thought they were turning the pipe. So if I can give you 50% of that back, I've given you ROP for almost free, right? All you have to do is change your parameters and get 1.5 days of rotation back into your drill string. Okay. If you change nothing, nothing will change. Right? And axial vibration, so this is the feature of the HD and the EMS. So now we can see instances of a bit bounce, if you like, and associated damage to drill beddings. Okay, so those are all tools that predict or measure vibration. This is the fleet of vibration mitigation equipment that NOV has. Okay? So I'm going to go through the V-stab, the NV400 subs, and the agitator, which is probably a little bit of an oddball, but there's a few SPE papers out there on its torsional reduction abilities. So without adding any tools at all, without increasing your costs in any way, the easiest thing to change that you can do tomorrow is parameters. Okay, so from the analysis that we've done, you can take those recommendations and go and plug them into your top drive or your driller and say, okay, if you're an American driller, it'd be called Bubba. So you say, okay, Bubba, I want you to put this much weight on and this much RPM through these formations, and then when you get to this formation, you want these parameters, and do it in a scientific way. So this data set here is from Cabinda in West Africa from Chevron. So what these represent here, this is stick slip, basically, up in the 20-odd%. This is maximum shock levels, and this is the RMS shock level. Sustained high levels of RMS shock are very damaging to your BHA. It's an indication of the energy that's being used up. Maximum shock, you can have one event that's catastrophic, or it may be that the BHA and tools can withstand it. Sustained RMS is always bad news. So this is the kind of bit that was coming out from those kind of wells, right? Severely wrung out, multiple bit runs, costing Chevron a lot of money. So as a bit company, when you see this kind of thing happening, your first instinct is to say, well, the bit needs to be made more durable because it wrung out. So what we'll do is, we'll put more cutters down through the nose and the shoulder, maybe add a blade, maybe reduce the cutter size. We need more density. So you do that, and they put it in the ground, and it comes out, and it looks like this. So they went through a spiral of making more and more durable designs and having the same dulls each and every time. Then they ran the black box. Okay? And we reduced the vibration signatures to these. This is the same scales, so very low level torsional, lateral and RMS levels, simply by changing the parameters and changing the bit design. So instead of going very heavy, multiple blade small cutters, we ended up with something like a 616. The reason being that the 616, it drills faster, so you don't have to put so much weight on it, because it was the weight that was buckling the drill pipe that was causing the torsional vibration. So they thought that the bit was ringing out because it wasn't durable enough. The bit was ringing out because of the torsional vibration, which was being caused by the drill pipe buckling. So we took away the drill pipe buckling by applying an aggressive bit, modifying the parameters, and taking it down to that. So what does that mean for them? Well, this is the first 7 wells drilled. Okay, the grey boxes represent the interval. The red boxes represent the number of hours. So they went from over 200 hours per section down to 75 hours per section. It's a constant learning process. So we halved the drilling time based on understanding of what their problems were. This is a V-stab. So I'll show you an animation of the V-stab, and then we'll talk about the performances here.
V-stab vibration dampening tools take off incrementally down as compared to conventional drilling assemblies. This animation will help describe its capabilities for use in many drilling applications. In conventional centric assemblies, motion and contact is controlled by stabilizer placement. While the amount of motion is somewhat controlled, the frequency of contact is actually amplified and results in frictional contact at multiple stages of the VHA. This results in a large amount of energy loss and additional torque to reverse bending stresses to the assembly. Sometimes this can lead to catastrophic tool failure. The V-stab, however, controls the contact at a fixed point when run in the correct place and under the recommended conditions. This fixed point helps eliminate multiple harmonic motions by instigating only the first harmonic mode, and thus forcing the system to control the forward synchronous flow. The motion maintains continuous contact with the wellbore, thereby providing virtually no change in acceleration of the component, which would result in shocks in the assembly. Due to the controlled motion, any randomly generated shocks can rapidly dissipate through the mass damping effect of the eccentric design and controlled motion of the tool. A side-by-side link in comparison of a concentric stabilizer and a V-stab demonstrates the motion of the tools in a wellbore under the exact same RPM. This animation is based directly off of laboratory tests and field data. The controlled motion of the V-stab adds wear to hard-based material on the tool, but does not allow the assembly to lose portal contact and thus instigate shocks, whereas the conventional assembly exhibits more of a backward or chaotic motion due to the contact interface with the wellbore and the blades. It should be noted that the V-stab is not meant to replace conventional stabilizers, but merely to help dampen the shocks and motions caused by the direction beat to run. The reduction of these shocks and motions result in more energy transfer to the bit, thereby providing an increase in our output. V-stab, a unique tool for drilling enhancement.
Right, so where this tool came from was a company called DPI, who made bicenter bits. And Reed Hycalog bought the DPI a number of years ago, and the tool came with it. And what they used to use the V-stab for was running behind bicenter bits, because the pass-through of the tool was smaller. It would go through the casing, and then they thought it would open up, and the blades, the V-blades, would contact the wellbore, and they would go around the wellbore like this, centralizing the VHA in the wellbore. And as you've seen from that animation, that's not how the tool works, but they didn't know that at the time. So occasionally, instead of running the bicenters on motors, they would be able to run the bicenter on a rotary application and be able to spin up the rotary to 120, 130 RPM, and notice that there was very little torsional vibration or stick slip happening when they did that. And it was a lot of trial and error and where you put the tool, so it didn't always work. So we spent in 2009, 2010, a lot of time understanding the mechanics of and physics of the tool and how it worked, and defining the operating parameters so that we can get forward synchronous whirl every time we run it. So here's a case study from the Gulf of Mexico. What we're looking at here is 5 wells, and they were drilled in order from right to left. So this is the last one drilled. It was the one with the V-stab in. And this, what we're looking at here, is the stick slip severity from the Schlumberger tools. You can see these first 3 wells have quite severe stick slip levels. This is ROP in black. In the 4th well, they seem to have a handle on the stick slip, but you'll see that from the next slide, it didn't really help them with the ROP. So basically, what we're looking at here is stick slip levels across the first 4 wells. You see, this one they managed to get down to 58%, but the ROP didn't really improve much from their average level. When they put the V-stab in, they managed to knock that down to 29%, and the ROP shot up to 176 feet an hour from about 110 feet an hour average before that. So once they took away that torsional vibration, the ROP went up by 60%. The V-stab has also got, as well as torsional mitigating properties, it also has lateral mitigating properties. So for BHA well, the forward synchronous well is an extremely stable form of vibration. Once you're in forward synchronous well, the ability for the BHA to go into backward or chaotic well is very slim. So if you can get the BHA into forward synchronous well, then you can avoid those type of things. So that was PDC well at full speed, not particularly good for the bit. This is drilling over gauge hole. This is damaging all of your gauge cutters, and obviously you're drilling an over gauge hole, which is costing you money. And then this is stick slip from one of our from the tool that came before Black Box. This was called the DRT, the Downhole Research Tool. And what they've done is they've taken the dynamics from the tool and they've animated it to show what the bit was actually doing. So this is slow motion. So here we have the bit stuck, then it speeds up and goes into the slip phase. Again, we've got some lateral movement, so we're drilling an over gauge hole. So it doesn't look too bad, but obviously when the bit's slowing down and doing this, you're not drilling. This is wasting money. Right? When you see it at full speed, you can see why stick slip is so damaging to the drill bit. So you're speeding up, you are potentially damaging the cutters mechanically because of impact, but you're also putting a lot of heat into the cutters, which is killing your PDC. Therefore, you wear them out prematurely. You don't get a full bite of the formation because as you torque up the string, it shortens. So you're taking weight off the cutters, it's unstabilized, you get the lateral motion. It's all in all a pretty bad idea. So the V-stab can get rid of your torsional and help with your lateral as well. The bending stresses associated with backward whirl are about 16 times more than they are associated with forward synchronous whirl. So if you've got whirl in your pipe, backward whirl in your drill pipe, that's when you're getting premature fatigue and your twist offs and failures. Think of it as a big flywheel. So here's the lab experiment showing how the tool works. So basically, this is going to be your top drive. You'll see this going around here at a constant RPM. The drill string is up through here. This is the BHA simulated. And then we have a second string here with a V-stab in it. There's a clutch here that's going to be driven from the BHA. So the only thing turning this V-stab is going to be top drive motion through the drill string from the BHA coupled to this. And you can see just how effective the V-stab is at getting rid of torsional vibration. So you look here, the constant RPM. Right? If you look at this coupling, you can see the BHA motion, which is in full stick slip. And then we'll kick in the V-stab. So this is now, the motion of this is it's like a big flywheel. It's using the mass of the BHA to break the BHA free. And also, if the BHA tries to slip, it's a big break. So it's like a two-pronged attack. So it's got mass inertia to help stop the stick phase, and it acts as a brake to slow down the slip frame. So these work best in holes up to about 45 degrees. Beyond 45 degrees, you often need more RPM from the top drive than it can give you, especially in small holes. But anything 12 and a quarter hole upwards, we have V-stabs that will work with most rigs. For the 8.5, if you're not vertical, then sometimes we can't get the RPM required. The only thing you need to run a V-stab is the required RPM. There's no weight on bit, there's no pressure, it's just a stabilizer that's a funny shape. Okay? So a lot of people will go out and pay $100,000 for an AST from Tomax. It's a waste of money, because this does the same thing and it's a lot cheaper, more cost effective. And here's an example of a V-stab in action again. This was Apache in Australia using GeoPilot. These are the shock signatures here. This is min, max and mean RPM from the tool. These are the lateral shocks being measured by their tools. At this point they tripped out, picked up a V-stab, went back in again with the same VHA essentially, cured the torsional, cured the lateral, took the ROP from 5 meters an hour to 14 meters an hour, because all the energy then went to the drill bit instead of the drill string. Yeah.
Do you use the same or different bit?
Yeah, it's not much different. Right. Whether you got a 616, which should be quicker than a 613.
Oh,
By what I know, right?
right.
But most other things were the same. So we've got some companies that run V-stab all the time. Like Pemex in Mexico, every 17.5 VHA they pick up has got a V-stab in it.
Yeah. So even though it's 15 mil cutter, which is in theoretically 13 mil cutter will drill slower than 16 mil cutter, will drill faster.
Yeah, 3 times quicker. Yeah, in theory. Well, we know that you could get a 616 that was slower depending on back brakes and whatever.
Right.
But generally, rule of thumb, the 13 mils should be slower. But
And use the less weight on it.
yeah. So that was Apache in Australia. So years ago, and there's a few guys in here who are probably not old enough to remember this, but Reed Hyclog developed a range of bits with steering wheels on them, okay, for lateral stability. When your bit is not laterally stable, that's what happens, right? That's a bit in whirl. You're drilling an overgauge hole. Some of these cutters are going backwards at times. PDC cutters are not designed to drill going backwards. They like going forwards. So when you start to move them backwards, they get broken, blades get broken, and generally you waste a lot of money drilling a big hole very slowly. So what we've done with our stabilizers basically is taken that ring technology and put it back into a different product. So this is what a borehole looks like that's been whirling. This is what a borehole looks like from the textbook. Right? The black box tools can actually detect this. We can look at the frequency from when we record the data in black box, every 20 minutes or so we will record a 10-second burst of data at 400 hertz or at 800 hertz. And from that we can do a frequency plot, and we can look at a dominant frequency, say if it's a 20.2 hertz. So we'll look at the number of blades on the bit, we look at the RPM the bit was rotating, and it will give us the frequency that whirl would have occurred at. And if the two line up, we know that bit was whirling at that point. So we can tell you if you're likely to have a hole that looks like this downhole as well. This is just wasting money. That's what we want. So we put the ring onto a series of stabilizers, so near bit or string. And what this does basically, it improves the lateral stability of the bit immensely. So in this case from Algeria, this was the caliper log with a conventional near bit stabilizer. At this point they tripped out and picked up one of these, and that's the caliper log afterwards. Improved ROP by 43%, because now we're drilling a circular hole and we're not drilling a funny star shape anymore. The Typically they went from a 1-3, 1-4 dull condition on the bit to a 0-1, something like that. Very bottom is a 300-foot section of very abrasive sandstones, right, for the Minjur formation. Only 10% of anybody's bits have managed to drill this in one run. Okay, so shooter DD is a rarity, 1 in 10. Okay? Reed Hyperlog had never done it, ever, right? So in all the time we've been drilling in this is a $50 million business, just this one section in Saudi Arabia alone. Reed Hyperlog did not have a bit that was competitive in this section. Okay? So we went in with a new bit design with some innovative depth of cut control features on it, Helios cutters, okay, and some black box recorders, right? In Saudi, when you get a trial, if you don't chart in the top 5 positions, then you get $1 for your drill bit, okay? So every 6 months, Reed Hyperlog will come into Saudi Aramco with a new drill bit, running the bit and getting $1. Right? So it gets kind of painful after a while. So we knew we had to be in the top 5. Anyway, so the previous record was 32 feet an hour, something. So in our first run, we managed to get 37 feet an hour with our new bit design, Helios cutters, and we recorded what was going on with the black box. Then for the next 3 wells, we were given the opportunity to optimize our performance. Okay? So we added hemi drill motors, we added the near bit ring stabilizer technology, and again we measured everything using the black box HD and black box tool. Okay? So on the 3rd well, we set a record of almost 60 feet an hour. So from 4 wells, for having never done the section ever, we almost doubled the previous ROP from 32 to 60 feet an hour. And all that was understanding what was killing the performance, getting some cutter technology that we needed with Helios, making sure the bit was as stable as we could make it, making sure the VHA was as stable as we could make it, making sure we were turning the bit with enough power to keep the torque. Right? And so, a huge success just from the ADS service. Okay. So the oddball here, the agitator. So this is a tool that it's really designed to reduce static friction. It gently oscillates the drill pipe or the BHA, depending on where you place it. And by doing that, it breaks up the torsional vibration pattern. So this is what it's designed for, right? It gives you consistent weight on bit, improved tool face control, increased ROP, longer reaches, reduced, right? And it's kind of I suppose the torsional reduction is a byproduct. What you always get with it is increased ROP, but now you can get reduced torsional, so adding to the ROP as well. We have run these behind motors, on rotary assemblies and RSS assemblies. You just have to do a little bit of homework beforehand to make sure that the MWD operating frequency and the agitator frequency are far enough apart that they don't interfere with each other. It's easy to do and takes about 10 minutes. There's just a little bit of pre-work before that. So here's the agitator in action. MWD companies, DD companies will come and tell you that it will shake everything apart. It's not the case. In the shales in North America, almost every single well has an agitator on it. They can't drill without them. Right? So I guess 100,000 Americans can't be wrong, but they are Americans. So what we have here is you have an agitator tool inside some casing. They're going to pull it out using a forklift. It takes 1,850 pounds to break static friction, and then about 1,500 pounds to continue to pull that out. Okay? So here we've got the agitator turned on. We've got a Scotsman, and he's pulling at 150 pounds, and he's pulling that tool out of the casing. So you saw how violent that was, right? It's about a 2 to 3 G axial motion. That's all it is. So you're not going to get 50 G shaking everything apart. It's not how the tool works. Right. So if you just look at how much that's shaking, it's not shaking much at all, but it's enough. We now have a big business in Saudi Arabia fishing with agitators. When you get differentially stuck and your jars and everything don't work, they typically will call us after about 10 days, sometimes 2 weeks. I think we fished one out recently after 31 days or something, and they just latch onto it, pull up, start pumping, and that agitator will just vibrate that VHA out of the ground. So we've saved Saudi, I think we saved Saudi Aramco something like $20 million last year in lost VHAs. So you could argue that if you ran an agitator in the stream, you shouldn't get differentially stuck anyway. There's just some examples of the vibration reducing and ROP increasing abilities of the tool. Here you've got a 4 3/4 tool with a Halliburton geoforce motor. The sliding improved by 180% and 84% with the 2 previous welds. ROP up 39 and 25. Sticks at levels down 70% and nearly 60%. So some huge increases. Right? So really then, to summarise everything, we've got the ability to predict where your vibrations are most likely to occur, measure them using the black box tools, and then based on what we see with that, suggest some solutions based on NOV technology, other people's technology, or the a change in parameters and drilling practices. We can normally tell you who's on the break, okay? So at 5:30 every day when the tool pusher comes out and relieves the driller, things go wrong. Right? He has a different drilling style. So suddenly all your shocks will increase because he has a different way of using the brake. He'll apply all the weight on, lock the brake down, let it drill off, weight on, let it drill off, whereas the driller may have had a more smooth action, keeping a steady weight, keeping a steady torque at the bit. And you see that for half an hour, it all goes wrong. At midnight, when the drillers change, different things happen. We can look at off-bottom practices, going on to bottom practices, pick out the best ones, make that a roadmap or a procedure going forward. If you do it this way, you don't induce big lateral vibrations at the bit every time you go back on bottom. If you stage up the RPM, if you stage the pumps, whatever. So you can see all this happening because the granularity of the data is so high using the black box compared to MWD tools. And then finally, I guess, optimized by directing all that energy back to the bit as well. So that's the end of that presentation. Thank you very much. Any questions on the equipment or procedures or anything? Processes?
Kalau nggak salah, if I'm not wrong, back in 2000, before 2008, 2005, 6, 7, and 8, VICO used for 8.5 inch section. VICO used 5 to 90 to pass the G61 formation. And then after that, change the bit design actually to 616 until now. So, but it was, if I'm not wrong, again, but we can try to get the data out, the past data. So, if there's proof, so I think maybe we can make an analysis again to the parameters, to order the drilling things like the DHA and whatever it is. Maybe we can have a new design for the iron section with lighter set blade, or maybe like design with the same blade, 6 blade with 19 new cutters, but maybe the back rate will slightly increase or maybe with using less cutter, whatever it is. But then we have to put something above the bit, or maybe we can tweak the parameter. Because if I'm not wrong, if we this is typically the drilling trajectory. Yes.
And you've been using motors to drill this bit. Do you still put a bend on the motor when you're drilling vertical here?
Yeah, the smallest, not the smallest 150. Just for operation, yeah.
So, Leo probably doesn't know this because he wasn't there, but about 2 weeks ago we had a conference in Dubai, and we've got now a new set of design and analysis tools that up until this point we've always designed our bits to drill concentrically. Okay?
Yeah.
As we know, when you're on a bend, you're
That is concentric,
you're not
yeah.
drilling concentrically. Right?
It's just technique.
So it's a problem that's been known about, but it's quite a complicated thing to model. You can imagine. So now we've got the tools. We've just run the first bit design with those tools over in the US in the shales, because that's what it was designed for, with Chevron, and they have drilled the first time ever from shoe to TD. So they drilled the curve plus the lateral, the 2.38 bend or something, in a record run, replacing 3 bits. And I saw, Marisa passed me some information from a report that Pratama had done on the Badak 234.
Yeah,
Well, so it's got quite a lot of shoulder damage, and
Oh, yeah.
so this is what we typically see when you're drilling with bent motor, and it's because the cutter load. So it's not just about more cutters, less cutters. It's about the actual design of the bit, and we're now in a position where we can really analyse the basically the depth of cut of the bit as it rotates around. So if we look at this, basically what we're looking at, it's a 5-bladed bit, so each one of these boxes represents one of the blades.
Okay.
What we should see is consistent shapes across every blade. And that means that when you're drilling, each cutter is sharing the load, each cutter is taking an equal bite of the formation. Well, as we rotate that bit around, what we see is that on blade 2, we've got these 3 cutters engaged. On blade 3, we've got all of these cutters engaged. Whereas on the opposite side of the bit, you're not getting any reactive torque, so it has propensity to whirl backwards.